Hello guys, welcome on Tesla Adventures. Now in this video, I'll be discussing level 3 numericals which are based on elasticity, and this level 3 is for JEE Advanced as well as Nsep stage 1. So in the first question, you can see that it is given the data that human bones are elastic if the strain is less than 0.5%, and it is given that the Young's modulus of compression and for extension are different for human bones, and shear modulus is this. Now there is a leg bone of length 20 centimeter and cross section area of 3 centimeter square. We have to find out the maximum stretching force that can be applied on the leg bone so that it still remains elastic. So we know that F upon area is equal to strain into gamma. Now we are talking about stretching a bone. So F is equal to area into strain into gamma. Now the maximum force which human bone can bear without getting plastic would be calculated by the formula A into maximum strain into Young's modulus of extension, which is stretch, this one. So F max will be equal to the area is 3 into 10 raised to power minus 4 and strain, maximum strain is 0.5%, so it is 1 by 2 into 10 raised to power minus 2. Because it is given in percentage, we have to convert it into absolute strain. And it is also given that gamma for stretch is 16 into 10 raised to power 9. So F max will be equal to 8 into 3, which is 24 into 10 raised to power this is 3. So F max will be equal to 2.4 into 10 raised to power 4 newtons. Now, in the second case, it is given that a man of mass 60 kg jumps from a height of 10 meter on a concrete floor, and half of its momentum is absorbed by the impact of the floor on the particular bone. So the impact lasts for 0.02 seconds. So we have to verify that will this compressive stress will exceed the elastic limit or not. Now, we are given a height with which the man has jumped, and it has jumped from a height of 10 meter. So the velocity of the man after jump and at the time when it is just about to collide with the floor would be root 2 GH. So V will be root 2 into 10 into H. H is 10. So V will be equal to 10 root 2. Okay, now the momentum delta P of the man will be mv. So delta P will be equal to 60 into 10 root 2. So delta P will be equal to 600 root 2. Okay, now we can say that this is the change in momentum of the man, and it is given that half of this change in momentum is absorbed in the bone. So the half of this momentum is delta P absorbed by the bone is 300 root 2, and the time taken is 0.02 seconds. So force applied on the bone will be 300 root 2 momentum absorbed by the bone upon 0.02. So F will be equal to 3 into 10 raised to power 4 by root 2. This is the force which bone will be experiencing. Now we have to verify that will this force make the bone plastic. So let us first of all use the gamma. So we know that the gamma for compression is 9.4 into 10 raised to power 9. Now you can see that the force which will be applicable on the bones will be 3 into 10 raised to power 4 upon root 2. So the stress developed in the bones will be F upon area, and F is 3 into 10 raised to power 4 upon root 2, and area is 3 centimeter square, which is 3 into 10 raised to power minus 4. So this will be 0.707. 1 upon root 2 is 0.707 into 10 raised to power 8. Okay, so this is the stress developed on the bones, and now this stress will be equal to strain into Young's modulus, and we know that this force is compressing the bone, so it would be a compressive force, and therefore we have to use the gamma of compression, which is 9.4 into 10 raised to power 9. So it is 9.4 into 10 raised to power 9. So the strain developed in the bone will be equal to 0.707 into 10 raised to power minus 1. I have cancelled out this one and divided by 9.4. Now in percentage, strain will be equal to 0.707 upon 9.4 into 10 raised to power minus 1 into 100. So this will be 7.07 upon 9.4. Now obviously this is greater than 0.5%. We are already given in the question that the maximum elastic strain that bone can bear is 0.5%, and this is obviously greater than 0.5%. So therefore, in this question it is being asked that will the compressive stress exceed the elastic limit? So the answer will be yes. Okay, now in the next third question, in the third question it is given that how much shearing force will be needed to break the bone if the breaking strain is 5 degree. So we know that shear force upon area is equal to modulus of rigidity into strain. Now shear force F upon area is 3 into 10 raised to power minus 4 is equal to modulus of rigidity will be 10 raised to power 10. So this is 10 raised to power 10 and multiplied by the breaking strain is 5 degree. You should always remember that when shear strain is given in degrees, you have to convert it into radians. So to convert it into radians, we have to multiply it with pi by 180. So F will be equal to, this is 5 into 3 into 10 raised to power 5 into pi divided by 18. Okay, because this 10 raised to power minus 4 into 10 raised to power 10 will be equal to 10 raised to power 6, and 10 raised to power 6 upon this 0 of 180 will be 10 raised to power 5. Now this is equal to 5 by 6 pi into 10 raised to power 5. This will be equal to 2.6 into 10 raised to power 5. So this much force will be required to break the bone if shearing strain is 5 degree. Now we move on the next question. In this question, it is given that the elastic limit and the ultimate strength of the steel is this and this. Now elastic limit is that stress above which the steel would enter into plastic region, and it would not regain its original shape and size once it is deformed. And ultimate strength, as the name suggests, is the maximum stress which that material can bear without breaking. So these two data are given in the question, and there is a steel wire whose length is 10 meter and whose diameter of cross section is 2 mm, and it is subjected to a longitudinal tensile stress. Now the Young's modulus is given as this one, 2 into 10 raised to power 11, and we have to calculate the maximum elongation that can be produced in this steel wire without making it plastic, and the maximum force which is required, or the minimum force which is required to make the steel wire elastic, in fact plastic. So first of all, we know that elastic limit is 2.48 into 10 raised to power 8. So in some cases, students are not able to understand that whether this elastic limit is strain or stress. You can just see the unit. So unit is Pascal, and therefore this is stress. So this is stress, and it would be equal to delta L by L into gamma. Okay, so delta L will be equal to 2.48 into 10 raised to power 8 into L divided by gamma. So delta L will be 2.48 into 10 raised to power 8 into length is 10 meter and gamma is 2 into 10 raised to power 11. So this is 1.24 into 10 raised to power minus, in fact this is into 10 raised to power minus 2. So delta L will be equal to 1.24 centimeters. You can see that. Now the maximum force which we can apply, or the minimum force which we have to apply to make this wire as a plastic material. So the plastic material means that it does not regains its original shape and size when we deform it. So the minimum force required for this purpose is the force required so that the stress which is equal to the elastic limit is reached. So the force will be elastic limit stress 2.48 into 10 raised to power 8 into the area, and the area of this will be pi d square by 4. Now this minimum force required will be 2.48 into 10 raised to power 8 into 3.14 into d square is 4 into 10 raised to power minus 6 upon 4. Now you can see that this is 2.48 into F minimum is 2.48 into 3.14, and it would be equal to 7.79 into 10 raised to power 2. So this is 779 Newton. Okay, now if we move on the next question, then it is in part B. It is being asked that we have to calculate the maximum stretching force that can be applied without breaking this wire. So the breaking stress, or we can say that ultimate strength, is 4.89 into 10 raised to power 8, and this is equal to the maximum force which we can apply without breaking this wire upon area. Now again area is pi d square by 4. So F max will be equal to 4.89 into 3.14 into 10 raised to power 8 and into 10 raised to power minus 6. So this is equal to 4.89 into 3.14. This is 15.35 into 10 raised to power 2. So this is 1535 newtons. So this maximum force it can bear without breaking. Now we move on the next question. In this question, it is given that there is a steel ring which is to be fitted on this disc. The dimensions of disc are in such a way such that its radius is r and its thickness is d. This is thickness, and the inner radius of the ring is small r, and the outer this width of this ring is b, and this width of the ring is d. Now the outer radius of the ring is obviously r plus b, and the thickness of the ring is d, which is same. Now we have to fit this ring on the disc. So we will stretch this ring with some force, and we will try to fit it on the disc. So we have to find out the longitudinal stress developed in the ring, and we have to find out the tension force developed in the ring. So it is given that the Young's modulus of the ring is gamma. It is also mentioned in the question that after we are fitting this ring on the disc, then there is no change in B and D. So B and D remains fixed. Now you can imagine that after the ring fits on disc, then the outer radius of the ring, will be equal to or the inner radius, we can say, will be equal to capital R, because its inner surface would be the circumference of the disc, and the initial value of that inner radius was small r. So the longitudinal strain developed will be 2 pi r minus 2 pi small r upon 2 pi small r, change in length upon original length of the ring. So cancelling out this 2 pi with 2 pi, then it is r minus r by r. This is strain. And we know that strain is equal to stress upon area. So stress upon Young's modulus, in fact. So stress will be equal to r minus r by r into gamma. This is the stress developed in the ring. Now to find out the tension developed in the ring, you have to imagine one thing, that if we see that this ring, so we can see that this stress would be developed due to this tension. So you can imagine that there is a strip. This is a strip, and a tangential tension force will be acting on this strip like that. So if I draw this strip from the cross-sectional view, from this view, then you can see that the top surface of the strip has a length of B, this one, and its depth or its height of this strip will be equal to the D. You can see that. And the tension is acting on this strip in perpendicular direction. So the tension developed in this strip upon area will be equal to stress, and we have already calculated the stress, which is r minus r gamma by r. So tension will be equal to area into r minus r gamma by r. So area of this strip will be equal to B into D. So you can see that this is B into D into r minus r into gamma by r. This is the tension developed in the ring due to stretching it. Now we move on the next question. In this question, you can see that there is a water tank which is supported by 4 pillars. Now pillars are strong enough to sustain the 10 times of stress which is developed in them when the tank is completely full. An engineer decides to increase every dimension of the tank and the pillars by 100 times so as to store more water. So we have to justify his decision, that whether his decision is correct or incorrect. Now we have to assume that when he is increasing the dimension of the tank and that pillars, the material he is using in the construction is same. Now first of all, let us see that if the volume initially, the volume of tank is V, let's suppose V is the volume of tank, and therefore the mass of water in the tank will be V into rho, and the mg of water will be V rho g. Now the total stress sigma total will be mg by area, and this is the area. A is the area of cross section of each pillar. So if I am taking the area of cross section of each pillar, therefore let us divide this mg into 4 pillars. So the force which is acting on single pillar would be mg by 4. So the stress developed in the single pillar will be mg by 4a. Now you can see that the maximum stress which they can sustain is 10 times of the stress which is developed in them when the tank is completely filled. So the maximum stress is 10 times of mg by 4a. So the maximum stress will be equal to 5 mg by 2a. This is the maximum stress which they can bear. Now you can see that if finally let us use another ink. Finally, the volume of tank is in fact, if we assume the tank as a cubicle or any cuboidal, then each of its dimension is increased by 100 times. Okay, so 100, if we increase the dimension of the tank by 100 times, then you can see the volume of the tank will be increased by 10 to the power 6 times. So the final volume of the tank will be 10 to the power 6 into V. This is due to the fact that volume is length into breadth into height. So if each length, breadth and height is increased by 100 times, then the volume will be 10 to the power 6 times of the initial volume. Now this is the final volume of the tank. So the final mass of the water in the tank will be final weight, or I can say mg finally will be equal to 100 times of initial mg. In fact, 10 to the power 6 times, of initial mg. And similarly, he has also increased the area of cross section and the length of the pillars, because each dimensions of pillar is also increased by 100 times. Now if we distribute this force equally into all 4 pillars, then of sigma of single pillar now will be equal to 10 to the power 6 mg by 4 into area. Now the area of each pillar, if we increase the each dimension of pillar by 100 times, then area will become 10 to the power 4 times because area is proportional to the square of single dimension. So sigma developed in single pillar will be equal to, this is 10 to the power 2, which is 100 by 4 mg by area. Now you can see that this is mg by 4a is the stress which was initially developed in the pillars, and the maximum stress is this one, 5 mg by 2a. So you can see that this is equal to stress in single pillar is equal to 25 mg by A. And obviously the maximum stress depends on the material of the pillar. So the material of the pillar can bear a maximum stress of 5 mg by 2a, and in this case finally when he has increased all the dimensions by 100 times, then the stress developed in each pillar would be 25 mg by A, which is obviously greater than the initial maximum stress. So this idea would be not correct, and it would break the pillars, and therefore he should not do that. He should terminate, or he should abort the idea. Okay, this is not a correct idea. Now we move on the next question. In this question, you can see that there are two bars A and B which are of different materials, and they are in contact with each other. These bars are in contact at the junction, and the junction is making an angle of theta with the horizontal of bar. The area of cross section of each bar is S0, and it is given that if we apply a force, certain force, which is a force till these bars are in contact, and if we apply a certain maximum force, after which these bars will separate and this adhesive will not able to hold this bar. It is called as yield of adhesive, which means that adhesive will behave like a plastic material and it will begin to flow like fluids. So it means that adhesive would not be able to keep these bars in contact after that force. We have to find out that maximum force. So let us see that this F is the maximum force, and in this case, if you draw the diagram of bar A, then it would be like that, and this angle is theta. So you can see that this system would always remain at rest, therefore the total force acting on the system would be 0. And therefore the acceleration of each of the bar is 0, and we can say that on each bar the total force is 0. So if this bar is being pulled towards left side with a force F, then a necessary force F would be acting on this side, which is applied by adhesive, and adhesive is being pulled by this bar B. So this bar would remain at rest. Now we can see that this is the maximum stress, normal stress. So we can see there are two components of F, and this angle is theta and this angle is 90 minus theta. So this component would be F sine theta. This is F cos theta, and this component will be F sine theta. Now let's suppose that this area is S. So you can also see that this area is given as S0. So S sine theta is equal to S0. So S is equal to S0 by sine theta. Okay. So the maximum force, the maximum stress which adhesive can bear is sigma naught, and it would be equal to the perpendicular force upon area. So perpendicular force is F sine theta, and the area on which it is acting is S. So sigma naught is equal to F sine square theta by S naught, because we have substituted the value of S as S naught by sine theta. So sigma naught will be equal to F sine square theta by S naught. So the maximum F can be written as sigma naught S naught upon sine square theta. This is the value of maximum force which this adhesive can bear without yielding. Now we move on the next question. In this question, it is given that there is a very stiff bar AB of negligible mass, and it is suspended by two rods of brass and steel. The length of the bar is 2.5 L, and the steel rod has a length of L, and the brass rod has a length of 2L. The cross section area of the brass is 2R. In fact, cross section radius of the brass is 2R, and cross section radius of steel is R. There is a force F which is applied in the vertically downward direction on the bar AB from a distance of X from the end B. And after applying the force also, this bar AB remains horizontal. So it means that both these brass rod and steel rod has extended by the same length. So it is given that the ratio of Young's moduli of both of them is 2, which means that gamma of steel upon gamma of brass is 2. So we have to find out this x. Now let us first of all assume that the tension in the brass is T1 and tension in the steel is T2. So we know that the torque about this point, let's suppose this point is C. So torque about C will be 0 because rod remains horizontal, and therefore T1 into the length, this length is 5 by 2 L minus x, and this length is x. So T1 is T1 into 5 by 2L minus x is equal to T2 into x. And we also know that first of all, let us find out the ratio that T1 upon T2 is equal to x upon 5 by 2L minus x. And we also know that T1 plus T2 is equal to the total force F, neglecting the mass because it is not mentioned in the question. Now, by the ratio division, we can see that T1 will be equal to x upon 5L by 2, and T2 will be equal to 5L by 2 minus x upon 5L by 2 of F, obviously. Okay, so these are the values of T1 and T2. And we can say that stress in steel will be equal to T1 upon pi r square, while the stress in brass will be equal to T2. In fact, sorry, I have taken the tension in the steel as T2 and the tension in the brass as T1. So this is T1. So the area of cross section of the brass is 2r, in fact radius of cross section. So the area would be 4 pi r square. Now you can also see that strain in steel will be equal to let's suppose the system has moved down by a distance of y. So strain in steel will be y upon L, and strain in brass will be equal to y upon 2L. Now we know that the stress upon strain is Young's modulus. Therefore, for steel I am writing it down that stress of steel upon strain of steel will be T2 upon pi r square divided by strain in steel is y upon L, and this is the Young's modulus of steel, and T1 of brass upon 4 pi r square into the strain developed in brass, which is y upon 2L, and it is equal to gamma of brass. This is equation 1, this is equation 2. Now you can see that if we divide these two equations, then the terms will be cancelled out, and T2 by T1, this would be T2 by T1, and this is 2, so obviously there would be a 2 with T1, and you can see that pi r square into y and pi r square into y would be cancelled out, and there would be a 4 on the upper side. Here it is 4, and it would be equal to gamma s by gamma brass, so it is 2. So you can see that T2 is equal to T1 from this equation, and we know that T2 and T1 was these. So T2 is this one, 2F upon 5L, 2F upon 5L into 5L by 2 minus F, in fact minus X, and it would be equal to 2xf by 5l. Cancelling this with this one. So you can see that 2x is equal to 5l by 2, and therefore x is equal to 1.25l. So this is the correct answer which we were searching for, that for what value of x the extension in both the bars will be equal. Okay, now we move on the next question. In this question, it is given that there are two identical rods, one of steel and other of copper. They are stretched by the same amount. So extension on both of them is same. So we have to find out that which operation the more work will be required. Now we know that obviously for the gamma of steel is greater than the gamma of copper for obvious reasons, and as their dimensions are same, so we know that the the spring constant, elastic constant, we can say that if we assume each of the rod as a spring, so we know that the spring constant of those equivalent springs would be gamma A by L. Now the area and the length of each wire, each steel rod and the copper rod is same. So we can say that K of steel will be greater than K of this copper. And therefore the work done when we are stretching them with the same amount, so the work done will be equal to energy stored, and energy stored in this case will be equal to half kx square. So work done is proportional to, x is same for both of them, so work done is proportional to k. And obviously we know that K of steel is greater than K of copper. So work done in stretching the steel would be greater than the work done in the stretching copper. Now it's in part 2. It is given that these two identical rods of copper and steel are stretched with equal force. Then we have to find out the fact that on which operation more work done is required. So when force is same on both of them, then we know that the formula of energy stored or work done is equal to half F square by K. So this formula can easily be derived that half Kx square is the energy stored and X is equal to F by K. So U is equal to half K into F square by K square. So this is half F square by K. So you can see that in this case F is same and therefore U is inversely proportional to K. And K of steel is greater than K of copper. So the energy stored in or the work done in stretching this copper rod will be greater than the work done in stretching the steel rod in this case. Now we move on the next question. Now in this question you can see that there is a steel wire of cross-sectional radius r and it is stretched without tension along the straight line like that. Now its ends A and B are fixed on the wall and this wire is pulled into a shape of ACB, you can see that. Now this vertical displacement of the wire is D and the total length, this one is 2L. So this length is L and this is L. If the Young's modulus of the wire is gamma, so we have to find out the tension developed in the gamma. Now first of all, you can see that if we see that this length, let's suppose this is the initial length and this is L and this length is final length, this is L dash. So by applying Pythagoras theorem, you can see that this L dash would be equal to root of L square plus D square. And if we calculate the extension developed in single wire let's suppose AC. Then extension would be L dash minus L. Therefore, x will be equal to under root of L square plus D square minus L. And this x will be equal to, taking L as common, you can see that it is 1 plus D square by L square minus 1. Now x is equal to, L is common. We can apply binomial theorem, which says that if this term is very small, then its power is synthesized with this term, and it can be multiplied directly with this term. So this is its power is half, and you can see that we can write it as D square by 2L square minus 1. So cancelling out this 1 with 1, so x will be equal to D square by 2L. This is the extension developed. And therefore the strain developed in this wire AC will be extension upon its original length L. So the strain developed will be equal to D square by 2L square. And the tension stress will be equal to tension per unit area, and the radius of cross section of the wire is given as R. So the area of the wire would be pi R square, and therefore this stress is also equal to strain into gamma. So tension will be equal to strain into Young's modulus into pi R square. So T will be equal to D square by 2L square into Young's modulus into pi R square. This is the value of tension. Now in the second case, in the B case, we have to find out the value of pulling force F. You can see that if we draw a diagram like that, this one, and this is the final position of the wire. So this is D and this is L and T would be acting like that, and let's suppose this angle is alpha and this is alpha. So this is 2T cos alpha, which is almost equal to F. Now in these cases we always assume that we are pulling this wire with a infinitely small acceleration, which makes its acceleration to be 0 and its velocity is constant. So we can we can assume that F is equal to 2T cos alpha. Now you can see that the cos alpha will be equal to the original length, in fact base upon hypotenuse. So the base of this triangle is D and hypotenuse is this L dash, and for small d, L dash is approximately equal to L. So cos alpha can be written as D by L. So F will be equal to 2T into D by L. So you can see that this D is very, very smaller than L. Therefore, F is very small than T. Okay. So this is the comparison of F with T. Now we move on the next question. In this question, it is given that there is a uniform rod of length L, and this rod is rotated in the horizontal plane about a vertical axis with some angular velocity omega. Now we have to find out the increase in the length of the rod, and it is also given that the Young's modulus of the rod is gamma and its density is rho. Now let us see that why this rod will extend, and we can easily say that this rod will extend due to centrifugal pulling force acting on the rod. Now you can see that on this part of the rod, in fact at this point, the centrifugal pulling force will be due to this part. So on each other point, the centrifugal force would be different, and therefore it is variable. So we have to integrate the total strain. Now let us consider a point at a distance of x, and at this point let us suppose a small length of the rod dx. Now we know that at this point the centrifugal pulling force acting at this point will be due to this part of the rod. Now we know that if this is x, then this part will be L minus x, if L is the total length of the rod. And the centrifugal pulling force acting on this complete part will be concentrated at the center of mass. So we can assume that the centrifugal pulling force on concentrated at this point will be m dash, and the distance of this point from the axis of rotation. Now the distance of this point will be this x plus L minus x by 2. So this is L x plus L minus x by 2. And m dash is the mass of this part. So this is m dash into x plus, this would be equal to, this term will be equal to x plus L by 2. So this is x plus L by 2 into omega square. Now m dash is the mass of this part. So we can say that m mass is distributed on the complete length L, and the mass per unit length will be equal to m by L. So mass of this part will be m dash, and m dash will be equal to lambda into L minus x. So m dash will be equal to lambda, which is m by L into L minus x. So we can say that the centrifugal force acting F will be m dash, which is m by L into L minus x into x plus L by 2 into omega square. So F will be equal to m into L square minus x square upon 2L into omega square. This is the centrifugal force acting on this complete part, and this force is pulling this dx. Now the stress developed will be force upon area, and let us consider that the area of cross section of this rod is A. So stress is this, and it is equal to gamma into strain. Now let us see that due to this pulling force, centrifugal force, this length of the rod dx has extended by a length dy. So the extension in this length is dy and its original length is dx. So strain developed will be dy by dx. And dy, which is the extension in this part only, will be equal to F upon area into gamma into dx. Okay. Now dy will be equal to F upon area into gamma. So F is this, m into L square minus x square by 2L into omega square. So m into, this is L square minus x square into omega square divided by 2 into L, and this is area and this is gamma. So this is area A and this is gamma. Okay, and into dx. Now you can see that mass upon LA, this is mass upon volume and it is equal to density. So density is rho divided by 2 gamma into omega square, and this is L square minus x square into dx. The limit of this term will be from 0 to L, and the limit of extension will be 0 to delta L. We have assumed that dy is the extension in the small part dx only. So the total extension is delta L. So the total extension delta L will be rho omega square by 2 gamma, and this is L square into x, and this is x cube by 3. So you can see that this is limit is from 0 to L. So this is rho into omega square by 2 gamma into 2 L cube by 3. So you can see that cancelling this 2 with 2, this delta L will be finally equal to rho omega square L cube by 3 gamma. This is the extension in the rod. Now we move on the next question. In this question, you can see that there is a rectangular block and it is kept on a hard floor, which means that the base of this block is fixed. Now the height of this block is h and the area of the surface of the block is a. We have applied a force F on the top surface, and due to this force, this rectangular block is distorted like that, and sigma here is the stress developed in this block, and neta is the shear modulus of elasticity. So we have to prove that the work done by the shearing force is this one, sigma square by 2 neta into volume of the bar. So first of all, let us find out the sigma. So sigma is F upon area. And we know that the energy stored in the wire per unit volume is equal to half stress into strain. Okay, so this is half, stress is sigma, and strain can be written as stress upon shear modulus. So you can see that this is sigma square by 2 neta, and the work done is equal to energy stored, and energy will be equal to energy density. This is energy density into volume. So work done will be equal to sigma square by 2 neta into volume. So this is the work done in distorting this rectangular block. Now we move on the next question. In this question, you can see that there is a thin uniform rod of mass m and length L. It is free to rotate in the vertical plane about this axis, like that. The rod is released from this horizontal position, and we have to find out the shear stress developed at the center of the rod immediately when we have released this rod. We have to assume the area of cross section of rod as A, and we can treat this rod as thin rod. Now, first of all, you can see that the alpha, angular acceleration of this rod, will be mg into L by 2, and that would be equal to I alpha, and I will be ml square by 3, and alpha is the angular acceleration. So this is L, and therefore alpha is 3g by 2L. Now the center of, if we consider this part only, BC. So this part BC, or we can say that this part is MB. So on this part, the acceleration of its center of mass would be at a distance of 3L by 4. And therefore the acceleration of this rod MB will be equal to 3L by 4 alpha. So acceleration of this rod MB will be equal to 3L by 4, and alpha is 3G by 2L. So this is equal to 9G by 8. And let us draw the free body diagram of this part. So mg would be mg by 2 on this part. Okay, and m, in fact m is mass given, but I have assumed this point as m also. And some shear force would be acting on this part. Now let us assume that the shear force, now you can see that if this part was falling freely, then its acceleration should be g. But you can see that its acceleration is greater than g. So it is obvious that the shear force acting on this part will be greater than this. In fact, it would be acting in the downward direction, because this force will make its acceleration greater than the free fall acceleration. So we can say that F shear force plus mg by 2 is equal to, will be equal to m by 2, which is the mass of this part, into its acceleration, which is 9g by 8. So F shear will be equal to 9 mg by 16 minus mg by 2. So it is equal to F shear will be equal to mg by 16, and therefore shearing stress developed will be F upon area. So this is mg by 16a. So this is the required shear stress. Now we move on to the next question.